Welcome to this module, that is metamaterial as a sensor. In the last module, we have discussed the basic characteristics of a sensor. Some important characteristics were accuracy, precision, sensitivity, selectivity, stability, and many more we have discussed. And we have seen a brief introduction of a metamaterial. So, metamaterial is basically a engineered material which is showing the property that is not possible with the natural available material. So, naturally available material basically represents a positive permittivity and positive permeability, but if we can manage the permittivity and permeability, then we can classify the materials, or we can design the material which is showing the negative permittivity, negative permeability. So, this diagram basically showing the 4 quadrant. First quadrant is showing the DPS material, that is a double positive material. This type of material basically the naturally available material like dielectric, which support the wave propagation in a forward direction. Second quadrant is showing the ENG material, that is a negative permittivity material. This type of material basically shows the evanescent type of a propagation, means signal will not propagate in this type of structure, and that can be achieved by using the plasma types of a material. Third quadrant is showing the DNG type of a material, that is a double negative material. In this case, both epsilon and mu, that is a permittivity and permeability, both are negative. So, this type of material shows the backward propagation, where the Poynting vector and the energy propagation are moving in a opposite direction. Fourth quadrant is showing the MNG material, where permittivity is positive, but permeability is negative. This type of material also shows the evanescent type of a propagation, that is it means that it is not allowing the propagation in that particular material. So, based on the value of a permittivity and permeability, whether it is a positive or negative, whether both are negative, both are positive, or mu is negative or epsilon is negative, we can use this type of metamaterial in different types of application, like in a super lens, in clocking to make the particular structure invisible. We can design the metamaterial filter, we can design the antenna, or we can design the metamaterial absorber. So, as our course is basically related with the biomedical application, so here we will see that metamaterial based absorber can be used for identifying the cancerous tissues or normal tissues. So, as name suggests, that is a metamaterial absorber. So, the function of this absorber is to absorb the incoming electromagnetic waves. So, the absorptivity can be represented by this equation, that is A, that is representing the absorptivity, is given by the 1 minus R minus T, where R is representing the reflectivity, T is representing the transmittivity. So, as we can see that absorptivity is given by this equation, that is a 1 minus R minus T, where R is representing the reflection, T is representing the transmission. So, that can be represented in terms of a scattering parameter. S11 square is representing the reflection property, S12 is representing the transmission property. So, the purpose of this absorber is to absorb the incoming signal. So, as we know that if any signal is coming on the particular structure, then either it will be reflect or it will be transmitted to the another medium. but here we want the signal should absorb. So, for this, as for it is given in the formula also, if we want A maximum, then R and T should be minimum. So, for making the transmission 0, we can place the metallic layer beyond the structures, behind the structures. So, the transmission that is T or S12 will be 0. Now, our function is to minimize the S11, that is the reflection property. So, for making the reflection 0, the reflection coefficient is given by this equation, that is a Z omega minus eta naught divided by the Z omega plus eta naught, where this Z omega is representing the impedance of the proposed structure, that is the structure that is absorber, and eta naught is representing the characteristic impedance of the free space. So, as we can see that the reflection property depends on this equation, that is a Z omega minus eta naught divided by Z omega plus eta naught. So, if Z omega is approximately equal to the characteristic impedance of free space, then according to this equation R will be 0. So, our purpose is to make the impedance of proposed structure close to the impedance of a free space, and that can be achieved by making the or manipulating the permittivity and permeability of the proposed structure, that is the effective permittivity and effective permeability. So, here we can see that as we have seen earlier also, that the metamaterial derive their property from its specific shape, orientation and periodicity, not from the base material like metal or dielectric. So, here one metamaterial based absorber is proposed for the biomedical application. So, the function of absorber is to absorb the incoming signal by making the reflection and transmission nearly 0. So, this diagram is showing one design of a metamaterial based absorber used for the biomedical application. So, this is showing the front view and the side view of that particular design. So, the structure, as we can see in the side view, that this structure is consisting of a top metallic structure and bottom metal, and between the top and bottom metal there is some dielectric material, that is a substrate. So, the top and the bottom metal are patterned with gold having a conductivity of 4 into 10 to the power 7, while the dielectric material is gallium arsenide is used as the dielectric substrate having the loss tangent of 0.006 and a dielectric constant of 12.94. The height has been optimally chosen as a h is equal to 6 micrometer, so that it can work at the terahertz frequency. The top gold layer consists of the B is equal to 0.4 micrometer thick and CRRs having the radius of R is equal to 10 micrometer, which is responsible to work at the terahertz frequency. To present the electromagnetic wave transmission, the bottom layer has a thickness of T is equal to 2 micrometer, so that it is acting as a physical barrier for the electromagnetic wave. So, the transmission will be 0, and the side length of the unit cell is 102 micrometer. So, since it is a metamaterial absorber, so we have to observe its absorption frequency, and that absorption frequency is basically depending on the transmission and reflection characteristics. So, we have made the transmission nearly 0 by putting the metal sheet at the bottom of the structure, while by creating the electric and magnetic resonance which is depending on the dimension of the top metallic structures, we are creating the reflection 0. So, at that particular point where the reflection is 0 and transmission is already 0, we will get the absorption. So, this particular structure is showing the absorption nearly 3.75 terahertz, and this structure basically can be represented in terms of inductance and capacitance. So, this structure is basically behaving as a epsilon negative type of a metamaterial, and the resonance is a plasmonic type of a resonance. So, these images are representing basically the electric and magnetic property for this metamaterial based absorber, and it is also showing the parametric analysis, how the absorption frequency is changing with different types of design parameters. So, this diagram is basically representing the input impedance and effective permittivity and permeability with respect to the frequency, and this last curve is showing representing the variation of a resonance frequency shift with alteration in the refractive index of the incomposing medium, which is used to detect the cancerous cell. So, the refractive index has varied in the range of 1.3 to 1.40, and we are observing the variation in resonance frequency with respect to the variation in refractive index. So, here basically the basic concept is that the cancerous cells and the normal cells have a different permittivity and permeability property. So, this diagram is basically representing the resonance frequency of the absorber versus the refractive index. So, we have the researcher have placed the analyte above the metamaterial based absorber, and based on the property or refractive index of that analyte, the absorption frequency of metamaterial absorber has changed. So, it is basically representing the response to the variation in refractive index, and that refractive index is basically given by under root mu epsilon. So, refractive index is depending on the permittivity and permeability, and permittivity and permeability of cancerous and normal cells will be different. So, refractive index will different, and corresponding to the variation in refractive index, the resonance frequency of a metamaterial absorber will shift. So, this diagram is basically showing the variation of a absorption frequency or resonance frequency with respect to the variation in refractive index. So, as we can see clearly that if refractive index is varying from 1.3 to 1.40, then absorption frequency of a absorber is changing, then we can classify whether the cell is affected or not affected. So, as we have seen in the previous modules, that sensor have some characteristic through which it will be characterized. So, corresponding to this particular metamaterial absorber, okay, there are some characteristic like sensitivity, there is a figure of merit, quality factor. So, the sensitivity, as we have seen earlier, sensitivity represent the change in output with respect to the change in a input. So, here the input is change in a refractive index, and here output is change in a absorption frequency of a absorber. So, second characteristic is a figure of merit, and the figure of merit is basically is a ratio of a sensitivity to the full width half maximum, and another characteristic is a quality factor, that is a resonance frequency to the full width half maximum, where this full width half maximum is basically representing the point where absorptivity is reduced to the 50% as compared to the 100%. So these are some characteristics through which metamaterial based absorber for the biomedical applications are characterized. This is another design, as we have seen earlier also. Basically, the geometry or shape of the metallic structure will decide its property, but this is also the metamaterial based absorber, but here gear type of structure is used and there are two concentric rings are also used. So these concentric rings are responsible for the two resonances, and another third resonance is produced by the gear type of a structure. So here we can see that we are getting the three resonances where the